The objective of this practice was to know how to use the universal machine, this with the purpose of getting the properties of the materials in use. In this case, aluminum and steel and their resistance to tension and deformation according to the law of ASTM.
Okay, for the tensile test we use two materials. The first material we use is aluminum 6061. After we use the universal machine, we need to calculate two data, that is the calibration length and the initial transversal area. With the vernier, we calculate the calibration length, that is 2.9092 inches, and the initial area is 0.9095 inches squared. The velocity of the machine is 5 millimeters per minute, and with the graphics that the computer printed, we can see the ultimate charge and the charge at 0.2% of deformation. The charge at 0.2% of deformation is 7690 lbf, and the last charge is 9220 lbf. After we use the universal machine, we need to calculate the piece with the vernier. So for the final length, we have a data of 3.45 inches and a transversal final area of 0.120 inches squared. The second material we use is steel 1045. This material has a 0.45% of carbon, that is more resistant than aluminum. So before we use the machine, we need to calculate also the calibration length and the initial transversal area. With the vernier, we calculate this data. So for the calibration length, we have a 2.96 inches, and the initial transversal area, we have a result of 10.9079 inches squared. Also, the velocity of the machine is 5 millimeters per minute, and the charge at 0.2% of deformation is 21,300 lbf, and the last charge is 25,100 lbf. After we use the universal machine, we have a final length of 3.18 inches and a final transversal area of 0.141 inches squared. With this data, we calculate the same information with the same formulas for each data. Yeah.
In this part, we put our steel in the clamp of the universal machine. After that, we place the extensometer in the middle of our sample. Then in the computer, we wrote down the values in zero and the initial diameter of our sample. We started up the machine and it started to grab the force of the tube. When the lecture panel got to 10, we took away the extensometer and wait a few seconds for the sample to fulminate. In the next stage, we use aluminum 6061, in which we follow the same procedure of the steel. We put in the machine the calculations made before, using the diameter and length of our aluminum piece. In this case, we could observe that aluminum is more ductile than steel.
So in this graph of the tensile test, we can see that in the above part is the strain, and in this part it's a lot of force, in which we have to get the stress or the strain. In order to get that, we have to use the formula stress force over initial area. Then we can see a red line, which is the elastic zone, in which it separates with a black line. Before this one is the elastic zone, which means that if we get our model out, it will get to the original form. And In this point is where it changes and doesn't get to the original form. In the blue line is the plastic zone, and the green line is the maximum point after it breaks our piece. And in the black line is the fracture strength, where our piece gets into two parts. And to get the yield strength, we have to use the formula force over initial area, and also for the tensile stress. Yeah.
Seeing the properties and the results of our two pieces, we calculate the percent error, and we see that we have a potential and minimum error depending the information, but this is because we need to do more tests of these pieces. Comparing the results by the piece of aluminum and steel, we can determine that the steel is more resistant than the aluminum. This is because the steel 1045 has a 0.45% of carbon. This do the piece more resistant, but the aluminum 6061 is more ductile than the steel. That's the difference between them.
In the strain curve, the regions identified in the table are modulus of elasticity, which is the blue line that shows the behavior of the material when a force is applied. This value shows the changes with stress. The limit of elasticity is a straight line that shows the 0.2% of deformation. It shows the maximum tension that can have a material without suffering permanent deformations. To the left of this line is the elastic region, and to the right the plastic. After these ones is the resistance to the maximum tension, which is the green line. And to the last of the graph we can find a black line, which is the breaking point.
It is very important to know about the resistance of the materials, because if we design a car, we need to know what type of materials we need to use, like steel, aluminum, or plastic.
In this practice, we saw how the resistance can our piece be by a process of manufacture. Using the universal machine and doing the tensile test, we can determine how efficient can be our piece to use it.
In this practice, I learned how it's important to choose the correct materials in designing some products, because there is important the resistance, the ductility, and other things in the materials.
With this practice, we were able to learn about the use of machinery in the laboratory. But most of all, we could physically verify what was explained in class, which was to know how a material behaves when a force is applied, and how much it can resist, so we can choose the right material according to its use. It is important to make the right calculations, so it doesn't have repercussions in the industry.